Hi everyone, in this video we are going to derive an exact expression involving inverse hyperbolic cosine, exact expression for the capacitance of a pair of parallel cylindrical wires. Now in my last video we talked about how to derive an approximate expression in the case where the wires are separated by a large distance compared with their radii, and that allowed us to make the assumption that any charges that have built up on the wires are not interacting with each other that much because the wires are so far apart from each other, and therefore we were able to assume that the charge distribution on each wire was uniform and that the electric field produced by each wire was radially symmetric. Now, the closer the wires get to each other, the less good an approximation that's going to be. You can see that if the wires have opposite charges, the charges are going to attract towards each other and pile up towards the inner edge of the wires, and that's going to make the electric fields produced by each individual wire less and less symmetric, which is why we're going to get a different result in this video. The method that we're going to use is the method of images. I won't give the full background on this because it's something I've talked about in quite a few of my past videos, but the basic idea is that in a problem in electrostatics with conducting surfaces, as we have here at the surfaces of the wires, you try to replace the conductors, or at least some of the conductors, with equivalent point charges or line charges that will end up giving you the same boundary conditions. In other words, you get equipotential surfaces where the conductors are, and you thus sort of simplify the problem by reducing it to a set of equivalent point charges and line charges. Now, I guess it's pretty obvious from the symmetry of this problem that we are not going to be able to approximate or replace our cylindrical wires with point charges, and so the logical thing to do would be to try and replace them with line charges. So if I just sketch on some sort of hypothesized line charges that we think would be equivalent to the wires, given what I was saying earlier about the charges on each wire attracting towards each other because they're opposite, we could put one line charge here in replacement of the wire on the left and one line charge here on the right-hand wire, and I've drawn them so that they're sort of close to the inner edge of each wire to show that the charges are attracting towards each other. And let's give the one on the left a charge per unit length, linear charge density of minus lambda, and the one on the right a charge density of lambda, where we assume lambda is a positive quantity. Now, in problems about capacitance, if you're trying to find the capacitance of some particular geometry, remember that capacitance is defined as charge per unit potential difference or per unit voltage, and so the standard procedure is to first find the electric field between the conductors, then you integrate that to get the voltage. So our first step is going to be to find the electric field, and so we can start by considering the electric field of each individual line charge, and we've already done that in the last video actually. It follows pretty much directly from Gauss's law. The electric field due to a line charge is the charge per unit length lambda divided by 2 pi epsilon naught r, where r is the distance, it's the radial distance to your line charge. That comes from considering a Gaussian cylinder around one of your line charges. Now, because we're really interested in the potential rather than the electric field itself, if we're finding capacitance, we want to integrate that. Again, E is minus the gradient of V, electric field is minus the gradient of the potential, so V, the potential, is minus the line integral along some line between 2 points of the electric field. So we're going to do minus the integral of lambda over 2 pi epsilon naught r with respect to r, and we are going to integrate between limits which I'm going to call r naught and r, where r naught is just some reference position at which we say the potential is 0, right? Potential is only ever defined, remember, up to a constant. So r naught, it could be anything, it's just our 0 potential reference, and because I'm integrating up to some particular distance r, I should really turn these r's into r primes because this is now a dummy variable. But then when we do our integral, this is just like a 1 over r integral, integrates to natural log, we get our constant of lambda over 2 pi epsilon naught, and if we apply our various laws of logs, we conclude that this is equal to log of r naught over r. And you can confirm pretty easily that if you substitute r equals r naught, you get natural log of 1, which is just 0. So this is consistent with what we were saying about r naught being the position of zero potential, right? So anyway, that's for one line charge. We really want the total potential due to our system of line charges here. So let's say the total potential, we can just use the principle of superposition to add them together. You're going to get a factor of lambda over 2 pi epsilon naught, common to both of them because they have the same magnitude of linear charge density. And I'm going to write this as follows. So natural log of r naught over r plus, where r plus is the distance to your positively charged line charge, in other words, the one on the right. Then we're going to subtract the natural log term from the other line charge, subtract because it's negative, has the opposite sign. So we're going to subtract ln of r naught over r minus, where as you can probably figure out, r minus is the distance to the negatively charged line charge. And note that I have written r naught as the same quantity for both of those natural log terms. We don't have to do that. You could have a different zero potential reference for each of the individual charges if you wanted, but we're free to choose things however we want, and it's going to be a big simplification if we allow them to be the same. If you then apply your laws of logs, remember that you subtract logs, then you divide the arguments of the logs if you want to combine them into a single log, and so we can write this more simply as lambda over 2 pi epsilon naught times natural log of r minus over r plus. Again, we chose the r naughts to be the same, so they cancelled. And so this gives us a way to write down an implicit equation of a given equipotential surface, right? Which is important because we want to choose our line charges such that the surfaces of the original conductors are equipotential surfaces. If we just invert the log by multiplying through by 2 pi epsilon naught over lambda and exponentiating both sides, we arrive at the conclusion that r plus over r minus, the ratio of distances to each wire, is e to the power of 2 pi epsilon naught v over lambda. And this is an implicit equation of a given equipotential surface of potential v for your combined system of line charges. Now, for convenience, I'm going to define this exponentiated quantity as alpha. It's a dimensionless parameter. It's going to pop up a lot in our subsequent working, so we may as well give it a nice easy symbol. And because it's usually easier to work with squared distances than distances themselves, thanks to Pythagoras, we can write this as r minus squared divided by r plus squared is equal to alpha squared. Now, to gain some insight into what these equipotential surfaces actually look like, we should make this this equation here a little bit more concrete by introducing a coordinate system. And so I'm going to introduce a Cartesian coordinate system. I'm going to put the origin at the midpoint of the two conductors. Could be anywhere along the line that acts as the midpoint between them, because we're kind of assuming that they're infinitely long. But I'm just going to put it at the bottom of this diagram. Let's say the x-axis goes to the right. Let's say the z-axis goes up. And if we want a right-handed coordinate system, your y-axis is going to be pointing into the page. And then your two line charges, the equations of those line charges are just going to be x equals a constant. Let's say that the equation of your positive line charge is x equals k, where k is some positive quantity, and the equation of your negative line charge is x equals minus k, right? Because we put the origin of the coordinate system at the midpoint, so the x coordinates of your line charges are going to be equal in magnitude but opposite in sign. Now, in this coordinate system, you can use Pythagoras to write down r minus and r plus in terms of x, y, z, and k at any arbitrary point in 3D space given by x, y, and z, right? So if we think about r minus squared first, the distance r minus squared is going to simply be x plus k all squared. Right? If you choose an arbitrary point with an x coordinate of x, you have to add on k, or equivalently subtract minus k, because your line charge already has an x coordinate of minus k. Square that, and we add on y squared, because the y coordinate of each of the line charges is just 0, so we don't have to subtract or add anything to that. And there is no z term, because if you move up and down along the z-axis, you're not changing the perpendicular distance to each line, right? So the numerator of your fraction in your r minus squared or r plus squared expression is just x plus k all squared plus y squared. And then by exactly the same logic, the bottom is going to just be x minus k squared plus y squared. And we're going to set that all equal to alpha squared, that constant term that we defined above. And at this point, there is going to be a little bit of algebra. So let's start by getting rid of the fraction, expand out some brackets, and let me write out some of these terms. We get x squared plus 2kx plus k squared from expanding the brackets, then plus y squared. I'm going to multiply the whole thing by the denominator and multiply through by alpha squared, and then your right hand side is going to be alpha squared x squared minus 2k alpha squared x, and then you're going to get your plus alpha squared k squared and then plus alpha squared y squared. We can then tidy this up a little bit by putting the x's and the y's on one side and the constant terms on the other side. We can also do some factorization. For example, if we put all the x squareds on the left-hand side, you've got 1x squared there, but you've also got alpha squared x squared, which is going to become negative on the other side. So overall, you have got 1 minus alpha squared x squared. Using the same reasoning, you've got plus 2k times 1 plus alpha squared times x, and then your y squared term is going to be the same as the x squared term. It's going to be 1 minus alpha squared as its coefficient, and then times y squared. The constant term, let's put that on the other side. We are going to get an alpha squared minus 1 all into k squared. And notice that this 1 minus alpha squared appears here, here, and here, but flipped around. And so this would probably look a bit nicer if we divided through by that. And we conclude that our equipotential surface has equation x squared plus 2k 1 plus alpha squared over 1 minus alpha squared x plus y squared is now just equal to minus k squared. And let's see if we can tidy up this 1 plus alpha squared over 1 minus alpha squared term. As it happens, there's a very convenient and neat way to write that using hyperbolic trig functions. So let's consider that term. It's 1 plus alpha squared over 1 minus alpha squared. I'm going to start by dividing the top and bottom of that fraction by alpha. Then we get 1 over alpha plus alpha over 1 over alpha minus alpha. Then if we put the definition of alpha in terms of this exponential up here, put that back into our fraction, we see that this is e to the minus 2 pi epsilon v over lambda, and then plus e to the positive 2 pi epsilon v over lambda. And then the denominator of this, I wonder if I can just copy and paste here, the denominator is going to be almost the same, but we just have a minus sign instead, right? So if I just change that plus into a minus, so here's your full expression for that fractional term. Now you may recognize the numerator of that fraction as 2 times the hyperbolic cosine of 2 pi epsilon naught v over lambda, and the denominator is almost 2 times the hyperbolic sine of the same argument, but the terms are the wrong way around, right? If we wanted that to be 2 times hyperbolic sine, then we would have to flip those two terms around. So the denominator is really minus 2 times the hyperbolic sine of 2 pi epsilon naught v over lambda. If you divide hyperbolic cos by hyperbolic sine, you get hyperbolic cotangent, right? Because it's like 1 over hyperbolic tangent. And so this all simplifies to minus cos hyperbolic tangent of 2 pi epsilon naught v over lambda. And I'm going to introduce another parameter for convenience here. I'm going to say this is just equal to minus hyperbolic cotangent of beta, where beta is just this whole parameter in the argument there. So that allows us to rewrite our x squared plus 2k, all of that stuff, x and so on equation in a much simpler way. It becomes x squared minus 2k cos beta times x plus y squared is minus k squared. Now, the meaning of this equation actually gets a little bit clearer if we complete the square and write the left-hand side as x minus k cos beta all squared, right? Because when you expand those squared brackets, you get x squared, you also get minus 2k x cos beta, which is what we want. There's an extra term as well when you expand the brackets, but we'll think about that in a second. Let's just put the plus y squared here. That's going to be, well, you've still got your minus k squared on the right hand side, but when you expand these brackets, you're going to get an additional term of plus k squared times cos squared of beta. So if that's now being added to the left hand side, we have to add it to the right hand side as well. So it can be written as k squared times cos squared of beta minus 1, if we factor that out. Then we can use a hyperbolic trig identity. Cos squared minus 1 is hyperbolic cosec squared. So we can write that as k squared times cosec hyperbolic squared of beta. That looks a little bit simpler if you're okay with hyperbolic trig functions. So if we've got this equals this, remember the right hand side for a given problem, right? This is a constant, right? The right hand side doesn't depend on x or y or z, and so the right hand side is a constant. Now if you have x minus something squared plus y squared is a constant, that looks very much like the equation of a circle, although really in this case it's a cylinder, right? It's like a circle that's being extended along the z-axis because there is no z dependence. Now what can we say about the cylinder defined by this implicit equation? Well, its center is basically given by this k cos beta, right? That's the offset given to the x values. So we can say the center is at an x value, which I'm going to call x naught, which is just k hyperbolic cot of beta. And what about the radius? Well, let's call the radius r. R is going to be the square root of everything on the right hand side, which is k. Now I'm going to put modulus signs here because hyperbolic cosec could be either negative or positive depending on whether beta and therefore whether the potential v itself is positive or negative. So when we square root the right hand side, we really want to put modulus signs. Radius has to be positive by definition, right? So k modulus of hyperbolic cosec of beta. And a slightly nicer way to, well, arguably slightly nicer way to write this is to put the modular signs into the argument. This works because hyperbolic cosec is an odd function. That means taking the modulus of the function itself is equivalent to taking the modulus of its argument. So we can say its radius is k times hyperbolic cosec. Going back to the definition of beta, we can say it's 2 pi epsilon naught over over lambda times the modulus of v, right? Because the only thing that may be negative is v. All of this stuff here has to be positive. So now we've got an expression for the center and radius of our cylinder. Now, one important consequence of this radius equation is that because of this modulus sign, there are two values of v that give cylinders of the same radius, right? That idea is going to become very important in a short while. But for any given value of the potential, the negative version of that potential, right, if you just switch its sign, you get an equipotential surface, which is a cylinder of the same radius. So just to summarize our key findings so far, we've said that for our two line charges at positions x equals plus or minus k with charges or charge densities plus or minus lambda, the equipotentials due to that system are cylinders, the center of each cylinder, and the radius of each cylinder for a particular specified value of the potential v is given by these two expressions that I've written at the top here. Notice in particular that the r has modulus signs around the v, but the coordinates of the center doesn't have that modulus sign. Now this is a good thing because we wanted to construct these line charges in such a way that we have equipotential surfaces on each of the cylindrical wires. The wires are cylinders, so it's perfect that we have actually got cylindrical equipotential surfaces. So now let's think about how to actually link all of this stuff back to the original parameters of the problem, which were that the wires have a radius of a each, and the separation between the centers of the wires is d. So just to clarify what's going on here, I'm going to write down. So let's suppose that we have r equals a because we want the radius of our equipotential surface to be a. That was the radius of one of the wires. Suppose r equals a on a particular equipotential surface which is V equals some specified value V naught, and we're going to assume for now that V naught is positive so that we can forget about the modular sign in the radius equation, right? Now, what implications does that have? Well, let's think about the, I guess, let's go for the radius equation first. Now, remember that hyperbolic cosec is 1 over hyperbolic sine. So if I just set this r equal to a, and multiply through by hyperbolic sine of all of this stuff and get rid of the modular signs because we're saying that V naught is positive, we get the following relationship. So k is equal to a times sine hyperbolic sine of 2 pi epsilon naught over lambda times V naught, right? So this tells us something about where we should place our line charge, right? If we want to have a particular equipotential surface, we have to choose k as defined in this equation, right? Now that we know what k should be, we can go to our center equation for x0 and just substitute all of this stuff in place of k as it appears in that equation there. So that tells us that x naught is equal to, I guess I can just copy and paste that entire expression. So all of that multiplied by, well, I guess I can do even more copying and pasting, copy all of this stuff. So cos of 2 pi epsilon naught over lambda, and this is now V0. Using the fact that hyperbolic cot is hyperbolic cos over hyperbolic sine, you will be able to see that this simplifies quite nicely just to a times cos, hyperbolic cos of 2 pi epsilon naught over lambda V naught, right? So we have fairly simple looking expressions for k, which says where the line charges have to go, and for x naught, which is the resulting center of the equipotential cylinder. Now here's where that fact I was saying earlier about the modular signs on this v in the radius is going to become important. So notice that there is another surface. The surface with v equals minus v naught, right, same magnitude but opposite sign, because of the modular sign in the radius expression, that is going to have the same radius, right? So there's some other equipotential surface with a negative value of the potential with the same radius. And where's the center going to be? The center is going to be, well, if you switch the sign of this v, because hyperbolic cotangent is an odd function of its argument, if you switch the sign of v, you also switch the sign of the function itself, which means x naught will also just get a minus sign, right? So the surface v equals minus v naught has the same radius as v equals plus v naught, but its center is now at minus x naught instead of plus x naught. That means you have these two equipotential surfaces, which are both cylinders of the same radius, have a total separation of 2x naught, right? Because the center of one of them is at x naught, the center of the other one is at minus x naught. You subtract those and you get 2x naught. But we know that the separation of the wires, the equipotential wires, was supposed to be d, right? That was one of the parameters of the original problem. And so we therefore need to choose our parameters such that 2x naught is equal to d, and therefore 2 times all of this, right? Let's make a note of this. So 2 times a cos 2 pi epsilon naught over lambda v naught has to be set equal to d. I'm going to rearrange this a little bit. I'll explain why I'm doing it this way in a few seconds, but I'm going to write it as 2v naught is equal to lambda over pi epsilon naught inverse cos minus 1 of d over 2a. Right, just done some multiplying and dividing and taking the inverse hyperbolic cos. Now the reason it's useful to have 2v naught on its own is that one of our equipotential surfaces has potential v naught, the other has potential minus v naught. Therefore the potential difference between them is just 2v naught, right? And therefore all of this stuff, lambda over pi epsilon naught inverse hyperbolic cos of d over 2a, is an expression for the potential difference between the two wires. So all we have to do really is plug that potential difference 2v naught into our definition of capacitance. Remember that capacitance is just charge per unit voltage. What we really want here is the capacitance per unit length, because the capacitance is proportional to the length. And so instead of charge per unit potential difference, we're going to do linear charge density per unit potential difference. So capacitance per unit length is lambda divided by 2v0. And when we do that division, the lambdas cancel out, and because v0 is on the bottom, we flip the whole thing upside down. We conclude that the capacitance per unit length is pi epsilon naught over inverse hyperbolic cosine of d over 2a, and we have therefore derived our exact expression for this capacitance per unit length. Now, it's always good to check, of course, that your exact results and your approximate results are in agreement with each other in certain limiting cases. I will leave it to you, the viewer, to confirm the details. However, all you have to do is notice that the definition of hyperbolic cos of some argument x is e to the x plus e to the minus x divided by 2. If x is very big, or equivalently in this problem, if d over a is very big, then the e to the minus x part of your cosh definition becomes very small, and cosh is roughly just e to the x divided by 2. And if we invert that, that means that inverse hyperbolic cos of x is roughly the same as natural log of 2x, right? And so in the limiting case where d becomes much bigger than a, this expression reduces to pi epsilon naught over log of d over a, which is exactly what we got last time. Okay, so that's all for this time. Thanks for watching, and see you again soon.